smooth these embeddings across the graph a bit, you enrich them, and you get better performance for that reason. Okay? So the way this works is we are given user item bipartite graph. We prepare shallow learnable embedding for every node. And then we use a multi-layer GNN to propagate embeddings across this bipartite graph. And then, in this sense, final embeddings are explicitly graph-aware. There are two kinds of learnable parameters that are jointly learned: the shallow user item embeddings, as well as the parameters of the GNN. Right? So here, the way we would do it, we would not first train the shallow embeddings and then the GNN, but we would kind of do it one after the other, right? Like we would basically do them in a coordinate descent type of way, so that we learn both at the same time. Okay? Now, about the initial node embeddings, we set a shallow learnable embeddings that basically are initial node features or node embeddings for every user. For every item, we initialize this embedding. And then we iteratively update node embeddings using this kind of neighborhood embeddings, where you say the embedding of a given node at the next iteration is a combination of the embedding of the same node at the previous iteration plus aggregation of the embeddings of neighbors. And here we have we are combining from items and we are combining from users, right? And different architectural choices are possible for the aggregation and combination. Aggregation could be mean, and combine can simply be like concatenation and some linear layer and then a non-linearity, right? So there's a lot kind of flexibility how exactly you implement this part. Okay, and then what are the final embeddings in the score function? After k rounds of this neighborhood aggregation, we get a final embedding h of u of k, and also the h of the item at k. And then what do? I say the embedding of the user is simply the embedding at the last iteration, and the embedding of the item is the embedding at the last iteration. And then score function, what people like to use is just the dot product between the embedding of the user and the embedding of the item. So to summarize what this neural graph collaborative filtering does, it's a conventional collaborative filtering method uses a shallow user item embeddings, and doesn't explicitly model the graph structure. So the GCF uses a GNN to propagate shallow embeddings across the graphs, and embeddings are explicitly aware of kind of higher order graph structure because of this propagation. That's the key innovation here, that you get the benefit of shallow embeddings, but also some smoothness or propagation of these shallow embeddings across the graph using this learnable GNN. Okay, that's the idea here. So that's the first method. I don't know. Do people have any questions? Or shall I show you the kind of a simplified version of this? Okay, I'll show you a simplified, and then please ask me a question. Okay. So the next method I want to show is called light GCN, and was also developed with recommender systems in mind. So here is how to think of this, right? The neural graph collaborative filtering jointly learns two kinds of parameters: the shallow user item embeddings and the GNN parameters. The observation is that these shallow learnable embeddings are kind of already quite expressive. All right, they are learned for every user and every item separately. And if you look at where are the free parameters, most of the free parameters are in the shallow embeddings, where the number of items, nodes, users is much bigger than the embedding dimensionality, right? Because the amount of parameters in the shallow embedding is n times d, and the GNN will have kind of this squared number of parameters, right? Or that order, right? So there is much more modeling power here than here. So what the intuition is that maybe these GNN parameters are not so essential in this. So the question is, can we simplify the GNN part and maybe make the model more efficient, easier to learn? And the answer is yes. And what people have also found is that actually it gives you a slight boost in performance, again, on benchmarks as well. So let's take a look at how does this work. The idea goes as follows. We are going to have an adjacency matrix for the bipartite graph. And I'm going to use the matrix formulation of the GCN, of the graph convolutional neural network, right? This is, I don't know, lecture 4, 5, something like that, right? Joshua was talking about this matrix formulation of a GCN. And then we are actually going to simplify the GCN by removing nonlinearity. And this is similar to this method that is called SGC, that is for scalable GNNs. And I think this lecture will come next week or in 2 weeks. Okay, so we are going to learn about this, and the two ideas are related. So let me now tell you about this light GCN. So we are going to take the adjacency matrix of an undirected bipartite graph. So the way the adjacency matrix of a bipartite graph looks like, there are 2 blocks of zeros because items don't link to items and users don't link to users. But there are non-zero entries here and here, and one is the transposed version of the other because the graph is undirected. Okay? Here, RUV is 1 if the user U interacts with item V, and 0 otherwise. And then we also have an embedding matrix that has the embeddings of all the users and the embeddings of all the items. Okay, that's the setting. So now I show you, try to kind of remind you what was the matrix formulation of a GCN. And the key concept here is this notion of a diffusion matrix. And another connection between the lecture today and what we are going to talk about now is the connection to this correct and smooth method. That was, I don't know, lecture 9 or something, where we talked about this semi-supervised correct and smooth method that was propagating the labels across the graph. And the key concept there was this notion of a diffusion matrix, where we have D to be a degree matrix. So this is a diagonal matrix that has degrees of nodes on the diagonal. And then we define this A tilde as a normalized adjacency matrix to be the degree matrix times the adjacency matrix times the properly processed degree matrix, okay? And then let E of k be the embedding matrix at the kth layer. And again, the embedding matrix is simply each row stores an embedding of a proper node. The difference here between the GCN, the original GCN formulation, is that here there is no self-connections, right? In the GCN, we added a self loop to every node. Here we don't, okay? And then each layer of GCN's aggregation can be written in the matrix form. This was that lecture that I was referring to, where basically you can take this diffusion matrix, embeddings at a layer k, the weight matrix to transform the embeddings, send it through a nonlinearity, and you get embeddings at the next layer. So that's kind of a matrix version of a graph neural network, where you work with the entire graph at once, and you propagate step by step from all the nodes using, here basically what happens is neighborhood aggregation, right? Because you are taking adjacency matrix and multiplying it with the embedding matrix. And these are the learnable linear transformations, right? So that's the idea here. So what does now light GCN does? Light GCN says, if you are iterating this equation up there and you remove the nonlinearity, right? I had a rel u here, now I removed it. And now my iteration says that ek plus 1 equals a tilde times ek times wk, right? Then the final, if I take this recursion and kind of expand it, then basically I say e of k is a tilde ek minus 1 times wk minus 1. So I can take this ek and throw it into that ek. So here is what I get, right? And now I can expand this and I get a tilde times ek minus 2 k minus 2 wk minus 1, okay? And you can see now that I can take this one and further further kind of unfold my recursion, okay? And at the end, when I have unrolled this all the way to the 0, this is what I will get, okay? I'll get this multiplications of a tilde k times, then I'll get the E0, the initial embeddings, and then I'll get these parameter matrices multiplied multiplied together, okay? But what's the point? The point is that this a tildes, this is just a tilde raised to the power of capital K. This E0 are the embeddings, and all these parameter matrices don't really matter because I can just collapse them together into a single parameter matrix, okay? So what this simplifies to, it simplifies to the following thing. It says that the embedding matrix at layer K is simply the a tilde raised to the power K times initial embeddings times parameter matrix W, okay? And this basically means that I'm diffusing node embeddings along the graph in a similar way that what correct and smooth did using the soft labels in the graph. So what's the algorithm? Algorithm that these people are proposing is that you are simply running this iteration. You take E, multiply it with a tilde to get new E, put it here, a tilde, and so on, right? So each matrix multiplication diffuses the current embeddings to one-hop neighbors. And note, right, that a to the k is a dense matrix. So if I run this as an iteration, this a raised to the power of k never really gets materialized, right? So I don't have to materialize this a tilde raised to the power of k, because this will become a very dense matrix because every power connects nodes that are 2 hops away. This was something I explained in the second lecture, if you guys remember, okay? So this basically iterative matrix vector product is useful to compute this expression, but much more scalable because I'm just doing this multiplication several times, okay? So this is the basic version of this algorithm. What people do in reality is they call what they say multi-scale diffusion, right? So what they say is let's weigh contribution from nodes that are farther out less than from the nodes that are close, okay? So the way they do it is they come up with these weights alpha 0, alpha 1, alpha 2, and so on. This is now multi-scale because these neighbors at different layers contribute different amount. And this includes embeddings diffused at kind of multi-hop scales. And this, alpha, here is how you can write it out, right? Like alpha 0 times E0 equals alpha 0, a tilde 0, and E0 acts as a self-connection that is omitted in the definition of a tilde. And the coefficients, this alpha 0 to alpha k, are hyperparameters. And what do people like to do? For example, just as a way to set these alpha parameters, LightGCN uses this uniform coefficient, where basically they say alpha k is just 1 minus k plus 1. So here, they would actually set the alpha to be the same for all alpha 0 to alpha capital K. Okay? So how does this work? Let me try to summarize this. So basically we are going to iteratively diffuse embedding matrix E using this A tilde matrix that I discussed, right? So from little k going from 0 to k minus 1, I'm going to take the the current embedding matrix, and then basically I'm going to multiply it with this normalized adjacency matrix A tilde with self-loop omitted to get the next level embedding matrix. And then I'm going to put this here and multiply again, and I'm going to iterate this for capital K number of steps. Yes?
Two questions. The first one is, if you are Amazon and you have 1 billion products, how are you doing this? I mean, are you doing this matrix multiplication all in memory? And then the second one is this related? Is this sort of like a generalization of the CATS matrix to the normalized adjacency matrix?
Two good questions. So the first question was about scale. Yeah, multiplying big matrices is not a problem. I don't know how to say. If you take my class in the spring, you'll see you can multiply really huge matrices if need be. You can even use MapReduce, and you can multiply the matrix describing the entire web and things like that. So this multiplication, yes, it's non-trivial, but you can do. What becomes a bottleneck is storing these embeddings. But you can distribute them across machines. You can distribute parts of this matrix across machines. You need some engineering, but it's very solvable. And then the second question was about CATS. Is this similar to CATS? Yes, it's similar, right? It's similar in a sense that in CATS we had these alphas as well, but they were decaying exponentially, right? And then there was this closed forum that we discussed. Here, these alphas are, these people decided to choose it this way. It's a good question why. It's a good question what would do if you do not Light's GCN, but you do a CATS GCN. It'd be cool to at least spend some time on Google Scholar and see if anyone has tried to do that. But it's an interesting question. So what the authors propose here is that basically you store all these intermediate embedding matrices, and at the end you just average them together, right? This is this uniform alpha, right? You just kind of average them together, and that gives you your final embedding matrix. Okay, so that's the overview of this method, where rather than iterating and taking the last one, you remember the intermediate ones as well, and average them up into your final embedding for the users and for the items. And then, as I said, the score function is simply a dot product. You take a user, you take an item, you dot product the two vectors, and that will be your score. Okay. So that's about this Light GCN that is kind of amazingly simple. You only take this adjacency matrix, you pre-process it using the degree matrix, and then you run the iteration, right? So the overview is you are given the adjacency matrix. You take this initial learnable embedding matrix E, right? So I use the shallow embedding matrix E that I learn ahead of time, and then basically all I need to do is take the adjacency matrix, normalize it to this A tilde, and then multiply this learned embedding matrix with itself a couple of times, and then average the results, right? So the Light GCN in this respect is a post-processing step, where in the first step I learn the shallow embeddings using the BPR loss or whatever, and then I propagate these embeddings or multiply them several times with the normalized adjacency matrix, average those resulting embedding matrices together to get kind of a better version of embeddings, right? So in this Light GCN, there is no learning after I learned the initial embeddings. Okay, so that's the key idea here, right? And why does this simple diffusion propagation work so well? The answer is that diffusion directly encourages the embeddings of similar users' items to be similar, right? So similar users share many common neighbors, items, and are in this respect expected to have similar future preferences, which means that when you are aggregating these embeddings from similar users and averaging them, you are in some sense amplifying this similarity between users. And you could make the same argument for items, is the two items are similar if they have a lot of users in common who interact with them. So that's the idea here. I maybe want to just make a quick comparison to kind of situate the light GCN and the original GCN and also the correct and smooth method and say what the differences were. Is that the embedding propagation in GCN is in light GCN is closely related to these other two methods. And in GCN and correct and smooth, the way we did it, we said that in terms of propagation, when we sum over the neighbors, we normalize the embeddings by the 1 over the square root of the product of the degrees of nodes U and node V. And we had the self loop to be kind of as part of this iteration. The light GCN uses kind of the same equation, except that the self loop is not added in the neighborhood definition. And final embedding takes the average from embeddings from all layers, right? So the final embedding is the sum of the individual layer embeddings, rather than saying the final embedding is the final layer embedding, right? So H of V is not H of V at capital K, but is a sum of H of V's for K's going from 0 up to capital K. So those are the two key differences. So with this, let me just summarize. What this light GCN did is it took this neural graph convolutional filtering by basically removing the learning parameters of the GNN, and now all the learnable parameters are in the shallow input node embeddings, and the diffusion propagation only involves matrix vector multiplication, and the simplification leads to a bit better empirical performance. So that's what I wanted to say about kind of the core two methods that we wanted to talk about today. I'm now happy to take questions. I see your hands. And what I'll do after the questions, I'll tell you about an industrial deployment of GNNs for recommendation systems. It's called PinSage, and this runs and was developed at Pinterest to a huge success, I would say. So I can say more. Yes.
Is there an intuition why the graph-aware embeddings are better than the one-hop embeddings? Because I think the intuition you provided, I didn't fully understand where the benefit is, given that it's like a bipartite graph. It seems like even with one-hop embeddings, you're getting like embeddings where the nodes are similar if their neighbors are similar. So is there an intuition for the type of graph-aware feature that you might be interested in?
Yes, good question. So why does this help? And the reason it helps is because it kind of smooths explicitly the embeddings across the graph a bit, right? And your objective function kind of doesn't enforce any smoothness, right? Doesn't explicitly say, hey, you have to be similar because you are connected, right? Yes, there is some term in there, but there is a lot of other terms as well. While these smoothing type things, they really kind of force embeddings to be more similar across connections. So I would say in some sense it smooths the data, it maybe denoises the data a bit, and that's why you get added benefit. It might be also that some users are very noisy, but you are still just training them based on their own data. But now because you take some other user, you kind of the information, it stabilizes the user itself. So it kind of averages the embeddings a bit across the graph, makes them more smooth, and actually makes them a bit more stable because of that. Yes?
Yeah, this idea of summing all your H vectors of all layers, can that, is this like specific to this type of problem, or can that also be like transferred to previous prediction tasks? Yeah, because it doesn't seem like specific to this.
Great question. Great question. So the question I'm repeating because I don't think people online are hearing. The question was this averaging of embeddings across layers is different than what we've been doing so far, because we always said, oh, the embedding is the final layer embedding, right? And you are saying, is this a general approach, or is this because it doesn't look like it's related to recommender systems? I would say, yes, you are correct. You could try this strategy elsewhere as well. Originally, it's been developed in the context of recommender systems, and that's also where it gives probably the best performance. But yeah, it's a more general idea. So that's a good observation. Anything else? Okay, so let me tell you about this PinSage or Pinterest recommender system that's graph-based. What is the idea? The idea is that given a query image, you want to recommend related images or related pins. And the way you want to do this is that you want to create this embedding of a pin, right? And a pin is not just the image. It also includes a description, like you see here, and it also includes the graph information. And for a while, this was the largest industrial deployment of GNNs that got hugely adopted across all kinds of products and surfaces across Pinterest, and it allows you to basically both do fresh content. So as soon as a new pin is created, it's basically embedded in this pin embedding space, and then these embeddings are consumed down the line. And the core of this approach is a graph convolutional neural network. And the goal is to create embeddings of nodes in a large-scale Pinterest graph, and I'm going to explain with tens, hundreds of billions of objects. And the key idea here was to really borrow information from nearby nodes. What happens if you only use visual information to train your models? Then you make mistakes like this, right? You confuse a steel fence for a rail of a bed. You confuse ground meat and soil. You confuse a rug and a tapestry. So you create these things that look visually the same but are semantically completely different. So it is essential to have a high quality embedding that you can then use for a lot of different tasks, for, from search to ads to content safety and so on and so forth. So now, how was this built, right? What is the key component of what Pinterest users do is that they you can think of it as they are like looking at these images and they are collecting them in different boards. So they are creating this bipartite graph between pins and boards. And board is just a collection of images, right? So maybe somebody's interested in men's style, how to dress well, and they are browsing images and say, oh, I like this one, I like that one, then they add them together. And then some other user, might be also collecting how men can dress well. And somebody else might be into plants, so they are collecting different arrangements of plants. And, somebody might be in architecture and so on and so forth. So we have billions of these boards where people kind of curate content. And especially if you're doing home remodeling, if you want to figure out how to throw a birthday party or something, usually people create a board and then browse and say, oh, these are ideas I like. It's almost like window shopping. Okay? So in this graph, we have two types of nodes. We have the pins and we have these boards, right? And the link is that a pin belongs to a board and a same pin can belong to multiple boards. And the graph has tens of billions of nodes and edges. And the way we create an embedding of a node is that basically especially of a pin, is that basically we have a GCN across this graph, right? At the bottom layer, we are going to have embeddings or features of individual pins. This would be images and so on. But then we have a GCN that aggregates this. So what this means is that the embedding of a given pin will depend on the embeddings of other pins that it shares boards with. And now you can basically back propagate into this GCN to learn how to optimally collect information from neighbors to create an embedding of a given object. And why does this help is because a garden fence is going to be pinned with other garden fences. Some of those garden fences will really look like a garden fence. So even the garden fence that seems to look like a bed railing will collect, embeddings of other garden fences and say, hey, actually, I'm not a bed rail, I'm a garden fence, right? And a bed will say, what am I pinned with? And it will be pinned with good-looking beds. So that bed will say, hey, I'm truly a bed, right? So that's kind of the intuition, what's happening here. And what's interesting in this work is that in addition to the model, the innovation, the paper introduces several methods to scale up GCN to this billion node scale and to the production workloads. And I'll give you a few examples. One was across negative samples, that there was a question earlier, especially around hard negatives, curriculum learning, and also mini batch training of GCNs, right? Usually people would have this matrix formulation of a GNN. This was one of the first papers that kind of said, hey, let's do the mini batch with the explicit sampling of the computation graphs and learning over that. So the way this system was supervised on a in some sense link prediction task, where the idea is that I want to recommend related pins to the user. So I have a query, I have a successful recommendation and an unsuccessful recommendation, and the objective function was that the distance between the query and the positive recommendation has to be smaller than the query and the sweater. So the GNNs will go this way, and then here is where the score gets computed, and then back propagation goes through this kind of two-tower architecture. In terms of training data, this was a few years back, but even then they were training on over a billion pairs. And here are some examples of positive training examples, right? And what's interesting is that sometimes, they might be quite different, but they are related, right? This is about sea, and this is sailors, here is Navy, even though, this is something to put on the door or something, and here's a mug, and so on and so forth. So they have a lot of examples of positive training pairs. One innovation to make this scale is this sharing of negative examples, right? That in a BPR loss, for every user in a mini batch, we sample one positive interaction and then a set of negative interactions. And using more negative samples per user improves recommendation performance, but also slows down training because you have to create these negative examples over and over again. So, right, if you want to have some number of positive users, then for each one you need to create some number of negative examples, and this can become quite expensive. Okay? So what is the idea? Idea is that we can share the negative examples across all users in the mini batch. So the idea is that while positive examples are user specific, now the negative examples are the same for all the users in the mini batch. This way, we only need to generate whatever is the number of negative examples embeddings for negative nodes, and we don't have to resample negative examples every time for each user. And this saves a lot of node embedding generation, a lot of computation, by basically the factor of the size of your mini batch. And empirically, the performance stays about similar, but you have just sped up your computation by a big big amount. So that's the first. And then the second one is this idea of hard negatives. And this goes to the questions I was getting earlier, right? That you basically, in these industrial recommender systems, you need to make these extremely fine-grained predictions, right? You have billions of items, but then you only care about top 10, top 100. So the issue is that shared negative examples, in principle, are randomly sampled from all users. So most of them are kind of easy negatives, right? It's so easy to recognize what's a positive example versus negative examples. So what you want to do is create this notion of a hard negative. And let me give you an idea, right? If this is a source, this is a query, and that's a positive example, right? Then if I just pick a random pin, it's some random cottage somewhere in the wood. It's very easy to say this is a positive pair and that's a negative pair. But this is an example of a hard negative example, right? It looks, so these are two, thank you very much, you are special type of cards. And this kind of looks like a card, but it's not. If you see, this is something you can put on a desk and it says happy birthday, right? So this is a hard negative example. And if I just have these random negatives, I'll be learning to make distinction between these two, and that's very easy. So I'll never learn to the level to say, oh, actually, this is not related. This is very different, okay? So you have this notion of hard negative examples. And the key insight is to apply this technique of curriculum learning, where you make negative examples gradually harder and harder as the process goes. So that the model kind of focuses on hard to distinguish parts of the space and really learns these fine-grained distinctions. There are a lot of heuristics how you set hard negative examples. At some point in time, they were saying, oh, let's look at, something that is ranked at rank 2000 to 5000 and maybe say that those are negative examples. But the correct way to do this is this distance-based sampling. So here is the key plot that I want to show to you. So this is the distance between examples, right? And if you do so this is distance 0, and this is kind of distance infinity. Think of it that way, right? If you do uniform sampling, then basically most of the pins are unrelated, so they'll be very far away. So your positive example is close, but then exists this gap, and then there are your negative examples. So if you do this hard negative examples that I showed you, then you sample from this region. So you have a positive example, this region, and that region. Again, it's not good. So, but if you use this distance weight sampling, then you kind of sample your negatives along the entire distance spectrum. And that really makes the model learn best, because you give it examples of all kinds of hardnesses, rather than giving it super easy or super hard examples. And if you do this, then you get really, really good results, right? So here's a query pin, and this is the visual embeddings, nearest neighbors, and here are the graph-based nearest neighbors. And you can see how basically, this is not bad, but this is definitely better, right? And you get some mistakes. So my last slide and then finish. So this pin sage uses GNN to generate high-quality user and item embeddings that capture rich node attributes as well as the graph structure. The key innovation was scaling and the notion of negative sampling. If you uncovered topic of this lecture is how do we scale GNNs up to large scale, and I'm going to talk about this either I think in the next 1 or 2 lectures. So this is what's yet coming, but I hope you like the lecture, and thank you so much.